Hello everyone, my name is P. Pawan Reddy. Today my presentation on navigation in a joystick environment fusion data from acoustic, optic and tactile sensors for autonomous mobile robot obstacle avoidance. Introduction. Autonomous mobile robots are increasingly deployed in complex, unstructured and often joystick environments from dynamic factory floors to unpredictable urban settings. Successfully navigating these spaces demands robust perception capabilities, and relying on a single sensor modality creates critical vulnerabilities for instance vision systems struggle in pure lighting or high glare conditions, while acoustic sensors can be overwhelmed and by ambient noise. Tactile sensors, while providing direct contact feedback, are reactive rather than proactive. And to ensure reliable and obstacle avoidance for and smooth, efficient navigation, the key lies in the intelligent integration of data from multiple complementary sensors. This presentation will detail the methodological and technological framework required to effectively fuse acoustic, optic, and tactile data, resulting in a significantly more resilient and adaptable navigation system for AMRs. And then addressing the limitations of single sensor systems. First one is environmental noise vulnerability. Acoustic sensors suffer significant performance degradation in environments with high ambient noise, leading to false readings or instead obstacles in environmental noise vulnerability. And lighting and visual ambiguity. In lighting and visual ability, optic sensors are highly susceptible to variations in lighting space or obstruction by dust, fog, or smoke, physical obstructions, and blind spots. In this, both acoustic and optic sensors can have field of view limitations or blind spots. Furthermore, they provide no information about close range contact, necessitating tactile input for ultimate safety margin. And last one is contextualization load and latency. High resolution optic data often requires substantial processing power, potentially introducing latency that is unacceptable for real-time speed navigation. Core objective for fusion-based navigation. Our research is driven by a clear set of engineering objectives aimed at creating highly reliable and performant autonomous navigation system. These are the types. First one is integrate diverse sensor suite. In this, we developed a hardware and software interface for seamlessly integrating acoustic, optic, and distributing distributed tactile sensors onto the mobile platform. The second one is enhance real-time perception. In this, improve the speed and accuracy of obstacle detection, tracking, and classification, especially for dynamic or purely illuminated objects. And third one is implement intelligent data fusion. In this, apply advanced probabilistic and machine learning techniques to merge and heterogeneous sensors data into a coherent environment model. And fourth one is guarantee robustness and safety, ensure fail safe operation and reliable performance. Sensor modulability deep dive. Understand the role and limitations of each sensor is crucial for effective fusion strategy. Acoustic sensors primary acoustics in acoustic sensors primary role is medium range proximity detection and coarse mapping. Benefits include low cost and robustness to lightning conditions. The key limitations is angular resolution and susceptibility to sound interference. They excel at providing quick, low latency range estimates. And then Optic sensors LiDAR provides highly accurate 3D spatial data for precise object location, and mapping cameras offer rich texture and semantic information. Their fusion is powerful but sensitive to adverse weather or lighting. And last one is tactile sensors installed on the robot's perimeter or manipulating ends. These provide immediate, highly favorable feedback on contact force and location. They serve as the last line of defense validation, optic or acoustic prediction at zero distance. And then advanced data fusion techniques. Data fusion is the algorithmic process that transfers noisy, fragmented sensors data into a single cohesive and reliable world model for the robot's decision making system. In this Kalman filtering, ideal for the tracking nodes, objects and state estimation, KF predicts the next state based on the current state and minimizes the covariance of the estimation error, particularly effective for fusion time series data like velocity and distance measurements from the acoustic and optic sensors. And then Bayesian networks and theory provides a probabilistic framework for combining discrete data and handling uncertainty. Uncertainty allows the system to model dependencies between different sensors, reading and calculate the probability of an object's existence or classification. Deep learning fusion, utilizing convolutional natural networks and recurrent neural networks for future level fusion, raw sensors input. Fusion is not merely averaging data, it is intelligently weighting inputs based on their current reliability concepts and introduce characteristics. This minimize of uncertainty is paramount for robust integrated system architecture. The overall the overall system structure includes decomposition and prioritized processing for real-time response, input stage, processing stage, and output stage. Central processing unit is responsible for running the fusion algorithm and the local planner, utilizes high performance hardware to manage the compute load from high bandwidth optic sensors. And then environmental mapping. The fused data generates a unfaded representation. Implementation pipeline from raw data to motion command. The successful deployment of a multi-sensor system requires a planned and executed pipeline to ensure data integrity and timely action. First one, sensor calibration and synchronization. Establish precise extrinsic and intrinsic parameters for all sensors. Critical step. Time synchronize all sensor data streams and then continuous data acquisition. Sensors continuously stream data at their maximum native frequency. And then third one is raw data peak processing. Raw inputs undergo filtering and normalization to bring all data. And then fusion data and obstacle analysis. The pure fusion algorithm combines the processed stream to generate a valid 3D environment map, classify detection objects and relate. And the last one is decision making and control. The planning layers utilizes the validated environment map to generate safe real-time navigation commands. Conclusion and future research directions. Reliability and adaptability. In reliability and adaptability, sensor fusion is proven to be an essential step toward achieving true reliability and adaptability in autonomous navigation. It creates a fault-tolerant system capable to operating effectively across a wider range of environment distributes. And the second is future work in AI-driven optimization. Immediate next steps involve integrating reinforcement learning to dynamically adjust the sensor weighting and parameters within the fusion algorithm based on robots context. And last one is application in human robot interaction. Enhanced environment awareness gained through fusion is critical for safe and efficient collaborative robots, enabling predictive collision avoidance and smooth interaction with human coworkers. Thank you.